Alright, welcome everybody. Day 32. What are we going to do today? I have done a little bit of renaming and rearranging of stream, sanitizer whole graph. There might be a couple nodes missing here and there, but nothing that is a big deal. So that we now have the guide for the leg global. If you open these, I'll distribute the scene. We have the actual leg global component, the god node here, the guide for the leg proper. I think this is not part of it. The interface between the two, the leg proper, and then the foot. So we are not in a bad place. It's at this point it's pretty clean. It's relatively easy to read still. The guide has added quite a few nodes, but 135 nodes, and that is more or less all the rig, and some of these that I've selected is CRUD. So, well played. I'm going to say 32, it's such a nice round number. I see what you did there. Now, I've done a lot of, wow. My daughter went full exorcist. She was crawling around at the speed of light. It's kind of scary, actually. Now, I noticed one thing. Laying it out like this, occasionally you gotta keep one of these under control. And if you start having tens of thousands of nodes, it obviously gets a little bit trickier, but you can do it just for adjacencies. Now, something that came out from doing these is, and I didn't want to do this off stream, is that the leg global word ankle. Now, this is what we're using for the one constraint here, the app vector that we use for the guide for the leg. So that is what gets us these in a cheaper way, because anyway we're gonna remove it when the component gets de-guided. Now, the reason why that is like that is that originally we did not have this raw ankle control thing, and then we added it for other reasons last episode. Now we also have this SRT that we're using for the blend, and these wants an SRT. Now let's fix that, I reckon, because this is crossing boundaries between components without going through an actual interface, which is not what we stipulated we will do. So rotate pivot translate. I don't use them. If you do, you'll need this, and you either need to cheat or you will have to expand the interface. And by the way, this gets de-guided away, so it's not a huge deal. Now, the problem is we're about to modularize the components so that we can export and re-import. So we can export one leg, import it again for the other side. And you know, if you look at longer term, obviously this is what gets you a library eventually. So no go, can't do things like crossing those boundaries. So these should be the entirety of the interface. There's clearly something going straight out. Tarsi angle, oh, okay, that's also fine probably, because I imagine that that is, yes, that is going out to the foot. We're okay with that. So that is legit. You know, and you might have to shuffle things around to see what boundaries you're crossing or not. Now, these uses the target translate and the target parent matrix, and it's not the inverse, it's a straight parent matrix, which we did a little bit of hackery so that we will get the parent matrix of these, which will be that, to multiply its translate. So we are fundamentally getting the word space of these. And I reckon that if you got no translate and just the word matrix, it will probably be equivalent. I just thought of this and I don't know if it works. What I was thinking of is I give it an ID matrix for the parent matrix, and I give it a translate from here. But I'm curious to see if I don't give it a translate at all. Translate, rotate. So this is properties of the constraint. Like, this is always confusing. The constraint is diagonal, so you see that stuff. Word up vector, we're cool. constraint rotate, constraint vector. Those are constraint parent inverse matrix. Yeah, that's also okay. This is what we are doing with the aim. So what are we giving it? Target translate. So my curiosity here is, if I just straight up give it the matrix and a 0 translate, will it blend? And is this translate that I'm giving it? Like, this is right now, this is at 0, 0, 1, 1, 1, 1. So I should be able, let's be brave. I should be able to do that. And then if I get the raw word, it's basically gonna be equivalent to what this by its parents word matrix would be. Life hacks. Oh boy. Those are two very distant plugs. Will it blend is the question. Who knows? It should. I mean, I don't know what they're doing, if one of the sports is static, if there is some trickery to it, but I can't see it being, you know, that weird. So if that is the case, the word vector doesn't really care about that factor. Let's have a look. My assumption is that these seems to work. There you go. Don't even need to translate. If you do it the way we did it, this is completely acyclic. This is necessary, and that's okay. Then the target, you know, wants all these things to respace it, but we're keeping those at 0 anyway. And we're just getting there. Yeah, I reckon we're good. I reckon this could work. We'll see. Maybe we'll pay in blood soon enough. But chat, as usual, you're my sounding board. Let me know if that is clear what we did. Rigging life hacks. But yeah, seems to be working. Okay, so that's taken care of. And this is the, sorry, basically I am segueing right into the modularizing part. Before you can modularize a component, you do have to make sure that you are respecting the interface boundaries and that, hi, and because otherwise, you know, it's going to come in all broken, and that it's properly containered for your ease of export. Once we have done that, just for testing, before we actually make it into a component that we're going to reuse, we're going to add an option to make it symmetrical, because we want that component, for our use case, we want that component to be capable of becoming mirrorable left and right, kinda. So what is left that is crossing boundaries? There might have been some stuff, because we say we would have been forgiving during authoring of some simple exceptions, but with the config parameters coming from another component or something like that, at a glance we got rid of all of it. Is it gonna be this easy? It never is easy. So we have a couple things like, again, resolution might be playing against us, but there's no container box here. The names seem alright. Not the bestest, but not too bad either. This is uncontainered. So if we've been diligent with the naming, in theory just selecting Lego from the filter will get us everything we need. I have done a passive naming. There you go. I have a compose matrix, which might be orphan. So yes, hopefully it was orphan. Didn't show anything, and that's set to have. Is it? Yeah. That's set to show more than just itself. It's more than 0, so that should be it. And this is the leg we're talking about. So normally, like, this is the kind of stuff you will do with a few scripts, to be honest. It will simplify your life a great deal. Now, we definitely don't want the foot input in there. And I'm gonna check that that is not doing something funky. So let's container the leg. Now, why was my foot input in the way? Ah, it's just at the edge of the selection and I already selected, so that's also good. There's bound to be other things non-containered, but we don't care. Not just yet. So this seems to be the entirety of our leg component, which I believe is the most complex we have. 81 nodes, including the CRUD, and the expectation is if I do something like that, I should see everything I expect in the master graph to be in this region. So that seems to also be okay. Now the other expectation is that if I select all of these, then, you know, I'm gonna get everything I select would appear in there. This is doing manually checks that you could easily instrument with the rig structure we use, but we don't want to do too much scripting too early. So this is actually interesting because I'm curious to see if it's used. Now all of my graph in theory should be pinned, except for that addition, so I can safely pin it. And I know I said I don't like pinning, and I still don't, but for the master graph with all the quirks that Maya has when it brings in nodes, you kind of have to. So that's going out to that, and that's the addition. Because this might be an orphan branch. This might be a branch that doesn't get anywhere. So pin that one as well, go out. No, it's not. Okay, so this is an active branch. Seems like something that we will want in this graph. This is the config. Going to those nodes. So seems legit. Also seems legit. This is receiving just from the config, and the config is for the most part being set up by the guide. So the guide is mostly receiving from over here. This is just noodling things around a bit to see if all the connections move where I would expect them to move. And when you do these, I mean, unless you want to space out the graph with the guides, you will have to accept that you have some OCD endangering stuff, such as this guide being like hanging all the way out. There doesn't seem to be any odd re-entrance. So at a guess we are good. So this is the SRT buffer. All right, sure. I don't have an undo view operation, but that's okay. Well, kind of. It also collapsed a lot of stuff that was carefully expanded, but oh, whatever. All right. Seems good. Stuff we wanted to add is pinned. This is in its own place. Here, we'll keep that layout. It's, you know, it looks sparse, but if we need to re-expand those nodes, will be good. So you can't save layout modifications. You need to dirty the camera before it gives you the asterisk. Don't trust it. Like, if there's no asterisk, don't trust it. There's actually stuff, hyper layout nodes, a lot of nodes that are flagged is not really having an effect on the scene that you might actually want to save. So that is done. Now the next thing to do will be selecting the container contents, and I need a mouse because right click is super finicky. Asset, select asset contents. So the asset should not contain itself. Leg L, FK start matrix. Where are tab? Everything is pinned. Let's see, we'll find out. Matrix in. Is this going anywhere? Huh. This is maybe at that branch? Nah, this is something that we used. Unless it's a longer that branch. FK start SRTs. Okay, this looks like something that we used to get to the blends or to the outputs. So one item was not containered. Could have inspected that at a glance, but that should be the last of it. I don't expect. So these steps have been running. I mean, you don't need to memorize them. It's just, you know, think logically for a little bit. You should get to it. If you have a well-ordered graph, you know, you start intersecting the names with selecting things here, with expanding that, looking at what happens, and eventually you should be able to sanitize the component by hand. If you do these a lot, as in if you adopt this workflow for your regular day-to-day, then I will strongly suggest you get yourself a few scripts. As you've seen with the guide, D-guide, like if you compare that to a lot of scripts that people write for their guides or to build their rigs, like this is a very easy way. Like this is a very easy rig standard if you want to instrument and augment with tools. So that is good. That goes in the leg container. Now my expectation is that this is gonna yield me everything I want. So everything in it is named leg L or is under something named leg L, where we say we're gonna be liberal with the form guide and control, because they're just hierarchy organizations, whereas input and output have a lot of active connections. So we chose to append the component name to it. Seems good. Seems good to me. It seems ready for export. And also important, it shouldn't contain anything from anywhere else. So if you zero that and expand to 1, does it have all the shapes as well? I might be not showing shapes. No, I was showing shapes. Okay, that's cool. So all the shapes are componentized as well. Now, when you do something like that and you want out, you would expect to have output and SRT. And word. Yes, that's okay. These connections, like I'll have to take a screenshot or something, because there's a few that we'll need to reference. But it's row ankle, rolled ankle. So these are named the same, shouldn't be too hard. And SRT, this is something normally I wouldn't do normally. This will be an attribute here. An up vector frame, which is up vector word coming out of this. That makes sense. On the other end, in the other corner, we should only, at the most, have the container, which is cool. Lego guide heap input, Lego guide, okay, so that's still itself. There should be other inputs if you add more than one output from this. In this case, we only output the foot. 2 parameters, that is a viable end, that is a trailing edge, and Lego femur and SRT, so that's good. So you can see that if you take this approach and you're fully non-reentrant, like whether you can use this layout or not, it doesn't really matter. That's not the point here. The time should be uncontainered. I don't think Maya would even let you do that, and it will probably reconnect that expression. But if you do something like that, once you just pull the container contents inside the node editor as they are, you instantly get a very clear leading edge and trailing edge for your component. If it looks scrambled and odd, normally means you have cross boundaries or you have reentrancy, but this is very, very easy to inspect, because you only have to look at these and these, and everything in between, you know, from your master graph. That is good. So belaboring the point a little bit, but this is the stream about modularizing, and this is kind of what it's about, which is knowing how to identify your module, how to sanitize your component. Again, once you know that, you can instrument it with some scripts if you wish, but not for us, sadly, not yet. So yeah, export time. All making sense? Let me know. Now, I've done this before. I've done it on stream. It's just not, again, not something I would know manually. So as I remember it, if you, sorry, I'm thinking for a second here. if you had these under something else, like if you had some character Uber thing, or if you had parenting and so on, before you export, Maya needs to build its full DAG paths for all these items. So it will often, or if not always, export anything that is above it. And that means that you can get accidentals like the siblings or something. So before you export, if you're using a hierarchy different, like not as like shallow as the one I use, you will need to parent these under the scene root. So unparent it basically. For the component, for the container, and this is something that I believe I have shown and discussed when we brought in the God node. If you want this to be a raw file with no containering, for whatever reason, then you just do not select the container and you're good. You select the container contents, you export those, and you're good to go. All the connections will be entirely self-serving. If you select the container when you export, you get a container component, which is what I want. So let's save that again. This is getting pretty twitchy reflexes wise, but let me also, so move that out just in case. That is just a shell, and I have shown it on stream before. So if you're curious, I will show you in a moment. And DB, there you go. So if you're used to Linux, which I am, and you need a shell on Windows, this is one of the easiest to install and manage, and it doesn't have everything you might want, and I don't know if it's maintained any longer. It's based on OMyZ shell, which is maintained, as is apt-get and all the package getters and all of that. This is called Baboon, B-A-B-U-N. So this is my database, and no. Okay, so what are we using here? We're gonna go and make ourselves a couple directories. And so deliverables is just where we're gonna put some milestones in, because at this point we have a long list. A long list of scenes, and you want to kind of save your milestones, and we are to the point where we're not just working on something, we're about to go outward facing with these. So ID09, not tabbing me? Okay, fine. What am I doing here? I can do it. So guide tweaks version 1.9. Okay. And let's say that in here this is so it's there and it's saved. Now to the export time. So if this reacts well to the export, then we are gonna look. Basically, we don't need to work, if it reacts well to the export, we don't need to work with this full environment where we have the foot depending on it and all of this stuff going into it. You can leave it disconnected and it will still work with the guide, because the stuff affecting the guide coming from outside would just be a constant, and you can expand that component without having to worry about, you know, this larger, messier picture kind of thing. If you export the hyper layout, actually, you get your bookmarks and the layout of the graph editor as well. But I am not gonna do that. I'm not gonna complicate things. Too much talking, not enough doing. So let's go. Export selection options. Now, what do you want here? Doesn't really matter. Ask your binary. Some people are superstitiously thinking that, you know, binary is broken or whatever. If you export whole rigs, I use binary, loads faster, it has a lot less issues. Sure, you can't humanly read it and humanly hack it. In that case, export doubles if you want. Preserve references. We don't have references, we don't care. Unload the references, don't care. Keep only reference, don't care. So this is what we care. If you include channels, expression, constraints, and all of this stuff, it doesn't mean that, you know, it's saving your connections here. It means that if you have something connected upstream, it will save that. So what I don't know, and we'll find out very quickly, is whether we need to save expressions. So not texture info, don't care, but whatever. Useful names for attributes on nodes. Oh, that's a file tab. That's just yeah, doesn't matter. So export selection and components lag. So that's done. Let's have a look at what it looks like. It's a bit redundant. That moment, like when you leave home and for holidays and you know you forgot something. There's that moment before doing a new scene without having saved first. So this is another bug I love. Is it? What is carrying it? This is so annoying. Yeah, whatever. At some point there must have been some active area side tab thing here. You're not... Nah. Wow, okay. Nice job, UI. Import or load doesn't really matter at this point. So, what we got here? Now, point number one, it came in at the right place. This is very good. Point number two, the guide still seems to work. Also very good. So it actually is that easy. That's, again, that's something I've been preaching for quite a while. If you have solid standards, even if they might seem like they introduce some busy work in your daily routine, you will have so much of an easier time doing everything else, such as validation, import, export, and so on. But you have to stick to the standards pretty tightly. So it brings stuff in component. It brings stuff in as namespace. Now, I am surprised that it brought in this much from the leg global. I suspect that I must have had something that was receiving from it or something like that. Leg global component. So let's graph that and see what... Whoa, I did not ask for that. And see what I get from it. It might even... Let's see. Okay. For all I know, those should not be doing anything. Maybe the initial shading group brought them in because... Oh, I know what happened. We're instancing these shapes. That's what happened. So this shape here that we're using as a diagnostic, I believe they're all instanced. And they're just, yeah, and they're just diagnostic. So Maya didn't do anything strictly wrong in this case. In fact, quite the opposite. It did the right thing. Well done, Maya. What happened is that this was an instance, which means it's the same as these nodes. So when it was looking for nodes to export, it was like, oh, I need these. And this is what I was talking about. If it finds that a node is in a hierarchy, it will get you everything up to the word. Now, we don't care for that. Do we? No, we don't. Go away. So that's it. Other than that, miss out. I mean, we don't care because we're gonna extend that component with the symmetry stuff anyway. Other than that, we're good. We might want to de-namespace it. But this is, again, this is not a bad thing because it's trivial to remove and it prevents. If you were to bring in the leg twice to test left and right, you will probably appreciate that namespace. Seems good. So there you go. Modularizing a component, you just do a little bit of work. And if you have strict standards and a shallow hierarchy, you use Maya's native export and it works. Where we head with time? 30 minutes in. Okay, so we're not doing too bad. I think that's all I wanted to get across for that. Now, might as well use these for an example. So, is it to shoot your eyes? It's about to get very white because I did not have a dark and mischief open. It's wide enough that it's projecting enough light behind me that it changes considerably the color of the green screen. So now, tiny bit of theory, and I don't remember if I mentioned this. Did I mention matrix handedness in the theory sessions before? Might still be good to do a refresher. So let's use, this is not going to zoom in. No, it's not. So you have this thing in Maya, y, z, x, y, z, whatever you want to read it like. And that is the word frame, the word transform, whatever you want to call it. It's always going to be an ID. It represents, you know, how everything basically shares a space. And that is quite simply could be represented as, and I think internally is, as a matrix. Now, let me check. So the way you see it there is X and Y and Z. It's pretty obvious. Now, pretty positive that I've done this before, but it's not a bad idea to redo it. Left and right hand matrices. So in some applications, actually, you could see it like that. And that is the difference between a left-handed matrix and a right-handed matrix. So very, and it's called like that because there's a very easy trick that's been around for a long time, which is you can do with the fingers in whatever order, but let's say that your thumb is X and you go in order X, Y, Z from the inside out. If your matrix has the X here and the Y here and the Z here, so I don't know, well, it makes sense to me visually, it might not to you because of the camera and all of that, but in Maya's case, looks like a right-handed matrix. Now, a left-handed matrix is the other way around. So what that means is basically, there's several implications to this, but the main one is that to produce the Z, remember how we say you can cross product two axes and get the orthogonal one, you will work in a counterclockwise direction. If you're in a left-handed matrix, to produce Z, you will work in a clockwise direction. And that is pretty much it. So there's the winding direction, if you want, of the angles. So that's left-handed and right-handed. A left-handed matrix, how sinister. Oh man, you're on fire today. Not necessarily in a good way. So that's left-handed and right-handed. Now, the reason I mention it is that very often people talk about negative scaling. I can't say I'm a huge fan of the notion, but here's another little bit of, you know, vector math. Now, vectors in general are, well, one way to think of vectors, and a pretty important one, is you have a basis for every vector. So you decide that there is one true vector somewhere. Might want to do it with colors that are more indicative of what we're doing. And all vectors that go down that line, let's say that this is our x basis, are scales of that vector. So if this is a unit vector of 1, this is our basis, and you can have different than that, but we're not going to do you know, changes in basis and so on. then there is an idea that every other x-aligned vector that is around anywhere on this line is nothing but this vector multiplied by a scalar. So if you have something like that, and you know, sometimes you hear people calling these floats or whatever. It's like float is just floating point number. It's just how computer science decides to describe non-integer real numbers. When you go into fields, so a vector is made of, you know, n numbers depending on your dimensionality. When this is a single number that can scale something, that's why it's called a scalar. So you have a basis vector and you have any other vector that is aligned to it is going to be a scalar. Now, this thing where I have to click harder to pick a color, it wants to, then I don't know if there's something where it wants more pressure to make sure you don't have accidental color picks. I can't draw a straight line to save my life today. Be easier if I flip the tablet and drew horizontally. But you get the idea. So, and it should be the same length. Ah, good Lord, help me. No, not gonna happen. Worse. This is frustrating. It's very frustrating. All right. Look, this is gonna be the same length as this one. So we have 0 and 1. That is going to be our y basis. Same exact thing. Any vector that is in y is going to be some portion of this. And it might be longer than that. So it's going to be this vector scale. So let's say that that's 0.4, whatever it is. Now, here is the interesting bit. So when we talk about, and we're 2-dimensional, 3-dimensional, 4-dimensional, whatever, it's always the same thing. When you have something like this, when you have a vector that goes like that, which is what we've seen in so far, you know, your position or whatever, these, you often see it, well, without often, like the way we've always seen it in so far, is going to be represented as a couple of numbers. We're in a 2-dimensional system. And what these numbers represent, when you think of, like, and it's easy enough to think, okay, this is the x portion of it and this is the y portion of it, but what are those? You have a basis. Those are how far along that basis you want to be. So they are a vector, the 2-dimensional vector in this case is 2 scalars because it is the terms, the scale terms of its basis. And maybe at this point you can imagine how a lot of transforms, but, you know, just so you know, don't need to understand or do it just yet. A lot of transforms, oftentimes, if you read papers or whatever, or if you started looking into vector maps, and fields and so on, you will find something like, oh, here's a new transform, and we had one before, and so on. So let's find the new basis. So if you move something like that and you decide that its child needs to follow whatever that parenting operation, its child is basically using the way you're used, the way you used to think of transforms. Its child is basically the basis for the transform, for the coordinates. Sorry, the parent is the basis for the coordinates that the child uses. That's one way to think about it. Hopefully that makes sense. Now, why did I mention all of this? Because very often people talk about negative scaling. Negative scaling is not incorrect, but then I also hear negative axis or negative vectors and so on. Not a fan of that. There is no such thing as a negative vector, because you have a basis, and it's possible that something described in that basis, such as a vector going here, sorry, might be, you know, 0.3 minus 0.3. So you have a negative scale on that axis, and whatever it is. What am I doing here? Yeah, that's... I might have these numbers wrong. Do I? No, 0.504, that's correct. So you might have 0... Oh, using... Damn me. minus 0.3 on the x and 0.5 on the y. So you do have one of the terms being negative because it's going this way, so it's a negative scalar. But vectors themselves, a lot of people think, okay, it's going in that direction, so the magnitude of the vector will be negative or something like that. The fact that one of the scalars is negative means that there's some negativity to it. And it's like, no. So you have quadrants or octants if you're in 3D or more than that. And you can think of this quadrant as just its scalar terms, or the scalar terms, the sign of the scalar terms tells you what quadrant you're in. So positive is 0. And you'll find this intriguing in a number of other cases. We're going counterclockwise, we have decided. So I know it might sound counterintuitive to some people, but that's how it is. So if you have your first minus here in the y, well, that was very wrong. I can do this eventually. Minus 0.3 in the parentheses here. So the first minus puts in this quadrant. If you add both negative, you know, minus, it will put you in this quadrant. And normally this would actually be number 1, 2, 3, and 4. I'm sorry. This has gone a little bit all over the place, but hopefully you are still with me. And you know, you wind back to having positive and negative. That gets you the 4th quadrant. So these are basically the foundational terms that you might need to understand how a vector is actually described. If you hear about a vector basis or a transform basis or a matrix basis, now you have an idea of what is going on. Now, when people talk about scaling negatively for controls, what is actually going on is that, and let's talk about when you want it. What is going on? Let's see, something that can indicate an orientation is that for something like an IK control, if we have 2 of these, cone 1 and cone 2, magical, normally, well, at least commonly, let's say, in my experience, animator want them to move together. And it's not a staggering majority. So and with together, I mean that they move in the same direction. However, with FK, people often want the movement to be mirrored. Now, that means that if you do something like that, their expectation is that you do something like that. Now, there's a couple ways to do it. There's a couple different ways to do it. One is so let's group that. And sorry, a bit slow here, but okay. Should have used other than default names, but whatever. So one of the things you could do is choose an axis that you're willing to sacrifice. And then at that point, and this actually gets, what am I looking at? So cool. I can do it eventually. Then you can do that. Now, what happens in that case is that their IK-like behavior, you know, the one we don't want is that they're separating as you go back and forth. They're doing that, so they're parting along one of the axes and they're symmetrical on the other. So the other thing that happens is that most of the rotation is well behaved and symmetrical, but not all of it. So you sacrifice one of the axes. And if you have something like this, it gets pretty tricky. Now, if something is constrained to a plane basically means that you can often give up an axis. So for, you know, something mechanical, or if you want this hybrid behavior, which very, very tiny portion of the people I know actually kind of like, don't ask me why, it doesn't make a lot of sense to me, then you can do it that way. It's that simple. But what is happening there is that your matrix for your basis, if you want, your transform basis, and this is why I mentioned it, because I don't want to use that word and confuse everybody, is invariant on the y is now equivalent to being negatively scaled. Negatively scaled, like when you're talking about vectors like this for the basis, is a thing, because it means you have the same scalar magnitude you had before, but its sign is now negative, so it's switch quadrant. And the same happens to the z. So what will happen here is that the winding of the, it's equivalent to having the winding of these changing. So that when you rotate the z, you get a similar orientation in the word, in example, because it's winding in the opposite direction. You've gone from counterclockwise here to clockwise here. Chat, help me out, because this is pretty important. Is it making sense? Now, for the x, that's a little bit trickier, because let's get rid of those. Is it trickier? Sorry, let me do it in my head for a second. So counterclockwise here will be that way, and counterclockwise here will be that way. So a lot of people have to try and transform all these things and put them into hierarchies and so on to figure out what is going on. And so do I, for the record. Having visual feedback, like especially when the transitions get pretty complicated, it can be tricky. But knowing what is going on, instead of going on about it in a purely experimental, empirical fashion, is pretty important. So is that the behavior we're observing? And if you go and look at the x, it's the one that is basically not, like it is now winding in opposite directions, but that's not what we intended, the way we were looking at it. Now, on the same note, the y here was winding counterclockwise like that, and the y here will be going counterclockwise like that, I believe. So might have been better if I, let's get some sense of direction from this silly cone. Never a good idea. Oh, you gonna make me do that? You are. Okay, seems that we have snapping on. That's not a bad thing in this case. So y also not what we wanted. Now, you can keep rotating axes and look at the winding orders and get a couple of axes that you want. Or you could invert the handedness of the matrix, and that is what happens when people scale negatively on just one axis. And oftentimes, and the reason why I'm mentioning all of this is that I see people learning a recipe of like, oh, if you put this object under this other object in this order with these things, then this magic happens where your controls are mirrored. Now, if you wanted to negate just the x so that you get a differently handed matrix, what am I doing here? Everything else stays the same. This thing is driving me nuts. It's like you have to click really hard to get a color change. If you wanted to negate just that, remember how we talked about how the matrix decomposition works and all of that stuff? You sort of want to do it in the word space. So if you have a parent over this matrix that's giving it its basis and so on, and you negate that parent, then you might not get the behavior you want, because that might be oriented in an odd way and you are inverting the handedness of its basis, but it might be off axis. So if that was transformed because it was going down in that direction, and you have some sort of buffer, locator group, whatever it is, on top of it, and you invert, and maybe that's what you want, and you invert the scale of this one, your handedness inversion, or your changing winding direction, or whatever you want to think of these as, is gonna happen on that axis. Now, very often, what people want, and this is kind of important because, oh, I did not want it to do that. It's kind of important because this is how you determine the behavior of this stuff, is where do you want this thing to mirror? Now, most of the time, what people want is that they actually want it to mirror, okay, sorry, I was pressing space because I'm coming from space navigation. What people want is some mirroring by some center. So in the case of our rig, you will need to do for this to work, you will need to apply this transformation that inverts the handedness. If this is, and FK makes it a little bit easier to do this, I guess. If these are, they need to be both in the same space for this to actually really work, or otherwise you have to do a little bit more additional work. It might be our COM, our center of mass, because we want the FK to follow the last bit. Now, the way to do it is actually super trivial. So if this is untransformed and you want an X scaling, let's say that this is our COM, then this is literally all you need to do. Provided, like, if you keep pivots and all of that out of it, it's pretty easy to deal with it. And I know a lot of you already knew about this, probably, maybe even most of you, but it's pretty easy to break unless, you know, your rig is really simple, or if you, in terms of, sorry, not your rig so much as your primitives. And that's why I don't use pivots, I don't use a lot of stuff, because it just makes the chain of operations a lot simpler. But it can still be fixed even in complicated cases. But you need to know the order of operations of what is going on with the pivots and the parents and all of that. And you need to make sure that what you're doing is finding your basis, the word that you want to mirror, and change the handedness of that. So once you do it, I know, I'm pretty sure this is not going to be surprising to a lot of people. But that is what is going on. Now, several caveat emptors with these, which is, it's important that you think of it as inverting the handedness and not scaling negatively on the -x, because that is not what is going to happen. When you do something like this matrix, the way it's shown here, as a basis, like to reach that basis, something influenced it. That matrix in its own terms will have its own basis and so on. It could be reached in different ways. So if you were, and now I would have to, let me think of it super quick. So if I took this matrix, rotated it around the, let's do it tabletop, and let's see if we can do it. If I rotated it by the Z, like that, for 180 degrees, that will put the X in that direction, and I'm not scaled negatively the X at this point, but the X is now facing the same as the other, well, this is now just a transform, as the other handedness, but the Y is still there. So then I will need to negatively scale the Y. So would that work the same? We can try. I don't know if I need a parent for that, but I'm tempted to say that you could make it work like that. And that also gives you your plane of symmetry, for the record. Now, that should be affecting it. So, now you have the same behavior. And that is why I'm saying you are not negatively scaling the X. It's important that you understand that operation. I'm sorry if I am belaboring this to death, but negative scaling is one of those things that I've seen treated, and rotations treated as black magic a lot. People trading this trick of what you do. There is no black magic to it. Your desire to provide symmetrical controls is that these two things and whatever follows have handedness that is opposite. Handedness is not a negative x, it's not a negative y or whatever. It means you're going from these to these or vice versa. And you can obtain in many ways. Now, the other reason why I am beating that horse to death is that it can get kind of tricky when you're dealing with matrices, and we do push around matrices a lot. In some ways it gets simpler because everything is pretty raw. In some other ways it can get a little bit tricky, because when you move these matrices around that you have come to think of as having a -1, and this is very tricky when you write animation tools that need to mirror between things. When you move these around, these matrix, as it goes out after we've inverted the handedness, these matrix used as a basis for something else has absolutely no, come on, you gotta be taking the piece. So I can do this. Mannys Click is driving me insane. So if click, damn it. If this is our word, and this is the child of that word, so this is the basis for everything, and you can't change it. Maya is handed that way, that's how it's gonna be. And you have a child that is supposed to be a hand inverted basis for what is gonna be your, man, I can't draw a straight line, for your FK controls from there on. As a matrix, this has no idea if it got there by doing x minus x multiplied by -1, or if it got there by doing 180 degrees in z and then y -1. So there is no such thing as a negatively scaled matrix. Is that making sense? This is what I wanted to get across. I was hoping to actually do some symmetry. I drifted off into all this theory. Basis vectors are kind of important. This understanding of changes in basis and what is going on and how it actually works. It's one of those things. Look, you don't need to understand all of the theory or apply it on a theoretical levels. You do, pen and paper exercises. But knowing more about it, knowing that this is the set of things might explain a lot if and when eventually you encounter problems and you go like, why is it not accepting my negative scaling? It's a change of basis, it's a change of transients, whatever you want to think of it as, and you have to manage it that way. So I reckon that's it. We did the modularization part. Not unhappy with that. Bit of nodding, bit of my explaining, my explaining, bit of theory. I reckon we call it. It's 1 hour in. Do we have any questions? I don't know what to add to this because it's been almost an hour square and I'm happy with it. Are there any gotchas that can trip you up, like passing inverse ended transforms to joints that influence meshes? That's a good question. You would have to try it because it's pretty specific. So yes, okay, that's a good question. There are gotchas. There are operations down the line, whether people implemented their own nodes, or even some of Maya's nodes don't always deal well with, people say, oh, this node or that operation doesn't deal with negative scaling, and it's like, no, it's very possible that if you look at something like emulating an orientation constraint, you are in a negatively scaled chain of sorts. You're building a word matrix, right? You're taking the parent, multiplying, you're doing all of this stuff. and you go, okay, you know, I have my, and this is kind of what we've done, I have my X pointing that way, is it? Well, the double cross product thing that some people mentioned, they did it. I'm going to project these here, and that's going to be my X. And then for the, come on. Oh, I know what's going on. That's why I was struggling. Wow. Okay. Sorry, it looked like it was crashing for a moment. And then what you do is you go and take those two and you cross product them by the winding order. So you go like, I know my handedness, I'm going to cross product them this way, because this is the winding order of my handedness, and you get a Z that way, right? You with me? Now maybe you didn't intend for the handedness to be inverted, back. Maybe you wanted the handedness that was transmitted from its parent, which this is possibly considering and, you know, doing its own inversions and so on. And this is now forcing its handedness on you. And there are nodes that do that. And a lot of people that write the simple nodes that make assumptions about handedness will give you that. So yes, there's a gotcha just in that. Occasionally you see something refusing your negative scale, and it's maybe the handedness is implied as that output something in some interim step. And to be honest, it is very tricky to write a node that will do that correctly by inheriting the handedness. Because if that change in handedness was coming from far up top, unless you want your node to look up its, you know, its ancestry, or to look up its parent and so on, it might be a long way away before you find that, you know, somebody chose to negate the X basis, or to rotate the negate if that has an effect on what you're doing. Or even just that the handedness changed. Now, if you have the parent matrix, the parent word matrix, you can find out the handedness of that, probably. So, but it's one more lookup that maybe you didn't want to deal with. And you suddenly you need to go, if you have a node like a constraint that takes several transforms to hook something out of it, who knows what it'll do, right? Do you consider the handedness of all of them? And there's, you know, you're switching quadrants, you're doing quadrant operations and so on. There might or might not be a right answer. Now, what nodes or deformers or whatever might specifically have an issue with that, I can't tell you. I can tell you there's ways to rig that make these a lot less painful, provided that you use somewhat complex bases, which is what I do when I deform, and they'll be probably a couple seasons away. But what that boils down to, I guess, is that do I want to go there? Probably have to at this point. No other navigation shortcuts. So let me think for a second. So things like scaling and so on. Here's the thing. If you have an arm that's going down that way, you know, with your control here, in skinning, and you have a cylinder bound to it, you know, the classic Maya thing. In skinning, you don't really have negative scaling. It doesn't make a lot of sense, because all you have is a vector here that will be transformed by a couple points. So if you start from a good basis where, you know, you have your twist nose, or you have a spine running down there, and you have your average stuff and all of that, dealing with it, your scaling is always going to be partial, and some skinning algorithms don't even deal with scaling, for the record. So if you wanted to restrict the whole thing, there isn't an obvious, oh, this thing is going to get scaled negatively, positively, or whatever. This thing, you know, each of these individual items will have to scale this way, same as all of them, to shrink the arm, but not on this axis, that will not be desirable. On this axis, to get that uniform scaling kind of thing, all they need to do is, if you wanted to scale down to something like this, all they will be doing, when you think about it, is translating to new positions that just happen to be, you know, their distance between each other will basically be scaled, but that is represented by their position, whereas the shrinking on these axes will be represented by their X scale or whatever. So when you do scaling rigs, well, at least when I do scaling rigs, which are tricky, I will never really just pass on those transforms unmitigated to the influences that actually drive the skinning. They normally tend to be several parameters that come into it. So there's, you know, the translation might be on a basis because you might have a spine here that's pulling them around, and that is a completely different transform than having a simple linear system kind of basis. And it will not have an issue with the scaling, because what you're scaling is the length of that as far as the spine running down this arm goes. You go like, okay, you look, it's, you know, it's been scaled down, now its length is shorter, and that's just the length that the curve should deal with. And then you would have, you know, the squeeze or stuff like that. It can get a bit tricky. There's also the problem that if you both scale and translate, which is, and a lot of people get that, so if you have a mesh here and you have its influence here, and these, no, its new position is here, and it's also actually, and it's also, sorry, let's say it's here, and it's also scaled up twice the size. Moving it there will basically take this and move it away there, and then scaling it to twice the size. If before to, you know, this point you had this offset, it basically doubles that offset. And most of the time, if you have a uniform enough cloud of influences, that works out alright. Sometimes you'll get some ungodly double transform like kind of stuff where, because stuff was displaced, your only expectation was that it would have scaled in place and offset things, but then it's also moving, and it's, you know, and you'll see it when you scale something up and you go like, oh, this is fattening in thickness a lot more than it's actually, you know, spacing apart. You start getting crinkles and stuff like that. Hopefully that makes sense. It's like, it's a little bit further ahead than where we're at, but the long story short is that it can be a lot of work to deal with scaling in rigs. Non-uniform scaling even worse, and you know, all kinds of stuff coming together. Scaling rigs are hard. Complex rigs that need to be scalable, especially if they need to be scalable non-uniformly, are very, very hard, especially to componentize. Do we have anything else, or we good? So we had a bit of modeling, bit of Maya, bit of theory. I reckon we call it a day, and we call it a good day. Yeah, that's it. All right. Thank you everybody for watching. And what is it today? It's Friday, so I don't think I'm gonna be streaming this weekend. If you're following this on YouTube, this is relevant to you. But I will probably stream one day next week. And then I'm on holiday for a little bit. And I reckon that in April we will finish this season. Cool. All right. Thanks everybody for watching, and I will see you